Okay, next up we have Chris Rogers, CEO of SensiML. Over to you, Chris.
Great, thanks, Ian. So as Ian mentioned, I'm CEO of SensiML. We are a software company that specializes in providing IoT device developers with the tools that they need to develop intelligent sensor models on their own that can build optimized code that runs on the smallest energy-constrained hardware at the IoT edge. And my purpose with this presentation today is to discuss some of the key practical considerations for using tinyML models for building real commercial products. So over the years, I would say we've had lots of experience with various customers, and the market's adoption of AI at the edge is still relatively early, but we're starting to see innovators and early adopters move from the POC and pilot phase into building products for actual real-world product offerings that they intend to commercially make available. So I wanted to share some of the insights that we had about how you transition from POC to actual product development for critical time-to-market product development. So a little bit of history quick about us. I won't spend too much time on this, just to say, in terms of our understanding and expertise in the area, we've been doing this for almost 10 years, initially with Intel. So we were a software tools group within Intel supporting their own silicon for wearable compute SoCs, ultra low power MCUs for industrial IoT, and had extended that capability over time. Intel ultimately exited the wearable business around 2017, and at that point then, we chose to take the product that we had developed and launched as Intel Knowledge Builder and continue to evolve that as a hardware agnostic tool and spin out as SensiML. So we've, since 2017, worked to continue to expand into additional applications, built out a partner network, and increase the number of supported platforms to include ST, NXP. We just announced today our partnership with Silicon Labs, and a growing list of other partners, including notably our parent company is QuickLogic, who builds a heterogeneous multi-core processor that has an MCU and combined with embedded FPGA logic. So in the case where you might want to be able to combine accelerated features with MCU computed or processed inference models, they've got some very interesting offerings as well. So if we look at the challenges that are involved in integrating AI with large-scale IoT deployments, where I might have thousands to tens of thousands or hundreds of thousands of sensors, the typical approaches have come with quite a bit of challenge, right? So the conventional way has been that the devices themselves are dumb data collectors, and they might do some simple data compression or other schemes in order to minimize the network bandwidth. But nonetheless, the aggregation of the data for centralized cloud processing is something that I think the market recognizes doesn't scale well. And as the types of devices we're talking about include image, audio, high frequency vibration, motion data, these sensors are becoming much richer. So it's not just temperature data or very simple types of sensors where that kind of transactional model works. So you need to go to a more distributed approach to address things like high latency. What happens with my insight if the network goes down? How do I partition the data so I'm not sending sensitive or private information to the network? Some of the things that were covered in some of the earlier presentations this hour. Second approach, deep learning, fantastic for some applications, and we're seeing purpose-built processors that include the acceleration for that. But still, in too many cases, we're talking about watts or tens of milliwatts worth of power, where in many cases the battery-powered devices that we look at are in the microwatt realm and need very efficient models that are power sipping, as well as the ability to rapidly build models without huge training data sets to converge. So there are other types of applications, notably time series use cases, where Deep learning isn't necessarily the only game in town or the best game in town. So there's a need to sort of look beyond just deep learning to the realm of all the other types of classifiers that are available in the market. And then thirdly, sort of the most traditional way is hand-coded algorithms, and I think most people recognize that doesn't scale. If you're doing step counting for a volume application like a wearable device, you might build that, but it doesn't give you a means to scale for all the other types of activities that a wearable device wants to be able to understand, right? So having human labor, whether that's in a consumer device or an industrial device that's doing anomaly detection, those types of approaches, while they might produce the most optimal code because they're hand-tuned, they just don't scale. So it's not really a viable approach for how to really grow the market. So if we looked in instead at how do you take the notion of tinyML and combine that with cloud processing, then I think we can look at sort of the best of both worlds where you've got ideal attributes. And there's a relatively new advancement in AutoML tools that optimize machine learning inference models purposely for ultra low power and resource constrained MCUs. And if you look at, for instance, the issue about, the network support, having something that can optimize specifically on the edge, even if offline, or provide real-time responsiveness, and allow for data processing partitioning for data privacy and security at the edge. There's some benefits in partitioning models that can run locally. AutoML models at the edge also have a wealth of different classifiers ideally. So the best tools are ones that can traverse a very large search space in the automation of searching for the optimal algorithm, not just looking at the weights and classifiers, but also the type of classifier being used, the types of feature pre-processing stages, and then even the triggering and segmentation algorithms being used. And then, finally, the avoidance of hand coding is really enabled by the kinds of tools that can automate that process using an AutoML approach, so that you're automating not just the model itself, but even the data collection and labeling tasks, which can be quite arduous and a tedious task to build out a quality data set. So when you combine that with cloud, then I think you see that you have a good partitioning where it's not a replacement for cloud. It's really a partitioning of the workload, so that at the edge, you're taking the high frequency data and providing insight and passing that to the cloud, where the cloud's context is in aggregating and having the broader picture to support dashboard types of analysis, where I'm in the health case, I'm looking at what are my session trends over time, what are population norms, and how do I compare to those norms? And that's the kind of processing that it seems makes more of a partitioned approach for cloud versus edge a sensible model. And then, that same approach applies whether it's an industrial and consumer, commercial, healthcare, or agriculture. So I think in all those cases, you can look at better user experiences where you're being smart about where you're partitioning, where the processing takes place. So as we're all here at tinyML, I think we understand that those benefits are certainly there. I think now what I wanted to do was focus on the key aspects and what we've learned over time that's important in ensuring that tools that you utilize for the edge, your AutoML tools, factor in some of these important aspects for building real-world devices. The first is that the model itself is really one that needs to encompass a full end-to-end workflow. So not just the core algorithm, but also the full work set, which I'll describe in the next slide a little more in detail. And that you have a comprehensive data labeling and data collection mechanism as part of your toolkit. What's equally important when you're trying to support real-world products and you have sustaining and issues that come up is that the code is transparent and flexible enough that you can adapt it and address corner cases as those arise beyond those things that you tested during the initial product development. And then finally, ensuring that your tools are ones that are built from the ground up to address the various domain experts that are part of your project, whether that be a firmware engineer or someone who's an application expert and understands the underlying data set that you're trying to properly classify. They all have somewhat different views of the problem, and the tools need to be such that they're not intimidating for users who aren't Python experts or data scientists to be able to still contribute their value in the process. The end-to-end workflow, if we look at the core modeling, that's a piece of the problem. The additional aspects of this are that you need model test and validation, you need data collection, and you need data segmentation such that you can support the entire workflow. And a lot of the tools, they focus on just the core modeling and code generation. So it puts the onus on the user to integrate and put together best-of-breed components for various aspects of this versus a lower risk approaches to ensure that you've got all of those encompassed in the tool that you select. The data sets themselves, those are as important as the modeling engine. We kind of look at and have seen time and again where it's garbage in, garbage out. If you have a wonderful classifier, but you've got inconsistently labeled data or insufficiently labeled data, then you're going to get poor results. So the tools that you work should support that notion of building bigger data sets and building them efficiently and being able to validate that you're in fact doing accurate data labeling. So what we have in the SensiML tool, for instance, are things like the ability to synchronize video along with time series sensor data, where it may be impossible or at least very difficult to understand what's going on just looking at the raw sensor signals. But that, and combined with synchronized video, gives you a good understanding of what's actually happening. And that you can label having multiple users contributing, where you have test technicians capturing data, but you might have domain experts who are actually doing the labeling phase of the work. And not only just doing the labeling, but also the metadata that's associated with explaining the variance in your model. So all of that is encompassed in a tool that supports the ability to build quality labeled data sets in the first place so that you'll have high quality models coming out of the process. The next step is that in the entire pipeline for the model itself, you want to have transparency in the code throughout at each of these stages. So ensuring that you have both the visibility as to what's happening in the model and that it's not a black box is super important when you're talking about actual products because you need to be able to explain your model and you need to be able to tune and support it. And then as your team's abilities grow, we have many customers who aren't AI experts, but they recognize that from a market compatibility standpoint, they have to have smarter products. And so they're dipping their toes in the water with AutoML-based tools that can help them build smart models without having that depth of experience. The key here is that the tools that you select should also have enough depth that you don't outgrow them as you acquire those skills or gain them yourself or bring on new experts on the team who have that capability. So you want to ensure that the usage model, the interaction, and the power of the tool also scales. And then the final point here is that you have various stakeholders that have various things that they contribute to the model building process. Ensure that your tools have the ability to allow those users to engage with the tool without steep learning curves involved that are outside sort of their normal domain and understanding. So with that, I think in this room, we're going to have the hangout session where we could actually get into more detail on some of these aspects. And then, of course, we welcome people to go to our website. A good starting point for these kinds of topics that I just covered is in our resources section, and explore our tool further. So with that, I guess I'll turn it over, see if there's any questions.
Chris, you mentioned AutoML a few times, and I was just wondering if you could say a little bit more about how you're viewing that within your current tool and your kind of the roadmap for your tools?
Yeah, so we're expanding out AutoML first from the standpoint of using AI to adapt the classifier hyperparameters itself, but also to look at feature engineering. For instance, we have almost 100 features in our library that go from simple like zero crossing to MFCC or fast Fourier transform. And without having to understand which of those features are valuable to get good class separation, you can have the tool basically use an automated search to go through that and find out what the right features are. Right? So those are two examples. The search space is potentially huge when you combine the selection of classifier, the selection of feature vector, the parameters, and then the segmentation algorithm. So over time, we'll continue to add more to that and encompass more of the potential search space.
Well, thanks.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.